AI, machine learning for robot motion planning. Embodied AI refers to agents learning to solve tasks through interaction with their physical environment. Today, we'll be presenting our results in this novel area of research, and we'll be focusing on state-of-the-art results in robot motion planning. This webinar is brought to you by Qualcomm and is a continuation of our webinar series on AI. My name is Amina Stepan. I'm part of the tech marketing team here at Qualcomm, and I'll be the moderator today. Before we get started, I'd like to show you how this webinar platform works. At the bottom of your screen, there are multiple application widgets you can use, including a widget to download today's presentation. All the widgets are resizable and movable. The slides will advance automatically throughout the event. At this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question in the Q&A widget and then click the Submit button. We'll answer questions after the presentation. Also, if you're experiencing any technical issues, please type your question into the Q&A widget and we will be glad to help. I would like to now introduce our presenter for today, Taco Cohen. He is a principal engineer at Qualcomm AI Research. His work in the field of equivariance and geometric algebra has earned him numerous PhD awards and fellowships, and his team's work in spherical CNNs was awarded the Best Paper Award at iClear 2018. Taco, please take it away.
Thanks, Armina, for the kind introduction. So I hope everyone can see my slides correctly. I'll just take that as a yes. So I'm going to be speaking today about embodied AI, machine learning for robot motion planning. So this is one of the important projects that we do in the interactive learning team that I lead within Qualcomm AI Research. So I'll start by talking a little bit about what embodied AI is and why it's important and why we as Qualcomm are interested in it. And then I'll zoom in on two research projects that we did recently in this space. One on the so-called geometric algebra transformer, which is a general architecture for geometric data as arises in robot applications, but also many other domains. We'll discuss one important application to robot motion planning. And I'll also just briefly discuss another project on affordance discovery. And then we'll have some time for Q&A. Okay, so embodied AI. What does the term mean? So we use this word to refer to an AI agent that interacts with and learns from some physical environment. So typically, you're thinking about something like a robot, as shown in this picture. But the word physical could also be interpreted a bit more broadly, thinking about agents in some virtual world, maybe in a metaverse type environment. But the important point is there's a space, and you're moving around in the space, and you have to learn how to operate the robot's body in order to achieve certain goals, as well as interact with other entities in the environment. So yeah, we're talking about agents. Could be robots, virtual assistants, or other intelligent systems. Another thing associated with embodied AI is perceptual inputs, right? There are many applications of AI, for instance, that deal with text or other non-sensor data. But with embodied AI, you're often talking about perceptual inputs, typically videos, could also be depth cameras, could be proprioceptive information about the particular configuration of the robot's joints, pressure sensors, sound, etc. And a very important distinctive feature is also that learning happens in an interactive fashion, meaning you're not just learning from a static data set that you can download off the internet. The agent is learning by interacting with the environment, by performing actions and seeing the result. This allows it also to learn what's called a world model. And a world model essentially is a generative model built on some of the same technology as the very popular image and text generative models, but it's a generative model that predicts how the world will change in response to the actions that you as an agent can take. And of course, the agent is pursuing some kind of goal. So we're trying to create agents that can learn to solve complex tasks, such as motion planning, navigation, etc., by interacting with their environment. Now, we envision that this will be very important for unlocking a lot of potential applications in different areas, from manufacturing, obviously very hot topic for the West to do a lot of reshoring and do more manufacturing at home. But with the present labor shortages, that's going to require a lot of automation. Also applications in healthcare, games and entertainment. And as you probably know already, today, a lot of the work in warehouses is done by robots. So we believe embodied AI can transform industries and improve lives. Now, I think it's interesting to contrast embodied AI with the previous or current generation of AI that I like to call Internet AI. So Internet AI is everything that you hear about and read about in the newspaper. The thing that's getting people currently excited because it's starting to work really well. Embodied AI, as I see it, is kind of the next frontier. There's still research to be done, but a huge amount of potential there. Now, where in Internet AI, one of the reasons it's been so successful is that it's based on massive data sets downloaded from the internet. So this started with, for instance, a famous ImageNet data set. It has been around for more than a decade now, but many similar data sets have been created. And this is essentially just a large static set of images along with labels of what's in the image. Or could be speech signals and transcriptions of the speech, or many of these types of data sets. And there's just a single fixed data set. And now the job of the machine learning researcher or developer is to predict one variable in the data set from another variable, to predict what is in the image based on the pixels of the image. This, as I mentioned, has been very successful, and a lot of AI technology is based around this paradigm. But embodied AI is a little bit different, because if you're trying to take as input or build a model that takes as input the sensor data that a robot might capture and should output the actions that the robot should take, you can't just download that from the internet. People don't upload that data to public social media accounts or other repositories. So this kind of data, for instance, egocentric visual data, so visual data as an individual or a robot would see it, rather than the third-person perspective that you often find in pictures, it's much harder to source. So there is a lack of good, high-quality data, and various parties are trying to address it, but I think this will continue to be an issue going forward. There's also some difference in terms of the goals. So with Internet AI, there's typically some narrowly defined specialized task that it can be thought of as pattern recognition. As I mentioned, image classification is a typical one. Text generation is another one. Whereas in embodied AI, the goal is to output the actions that an agent should perform. And this can happen in a variety of environments. So it's a very dynamic problem. On the other hand, Internet AI, its interaction with the physical environment is typically limited. So, you might have a system that can recognize objects and images, and you can use it to sort a user's photos or to create a collage on your phone of recent memories. Or you can do various things with it, but it's not yet a full package, not the full agent that you see in the sci-fi movies. Embodied AI has other issues. So I mentioned the data scarcity problem. Very important point to mention also is that whereas with Internet AI, there is definitely a trend towards running more and more of the inference on device. The cloud providers are happy to offload some of the usage to the user device. Users are also happy because it improves latency, it improves privacy. But still, a lot of inference is also done on the cloud when it comes to Internet AI. In embodied AI, you really don't have a choice, because when you're controlling a physical robot, then the frequency, the latency at which you have to operate is very, very low, very constrained, and so there simply isn't any time to go over the internet, have the server do a bunch of prediction, send back the results, and then execute it. By that time, your robot has fallen over. So that's not an option. On device is where it's at for embodied AI. Yeah, so there are many kinds of robotics, for everything from home assistants and cleaning robots to future applications like delivery drones, caregiver robots. Applications in agriculture are increasingly prevalent, public safety, etc. So we think this is really a big growth area and important for the company to continue to invest in. So when we think of a robot, we think of a couple things, right? We think of mobility. So the robot has to be able to move around. Sensing. There have to be, it has to get input about the state of its own body as well as the environment. And we think about intelligence, decision making, and ultimately autonomy, for the robot to decide on its own what the appropriate action in any given situation is. Now, it's a bit more motivation for why we need embodied AI. And robotics generally. I think we've all seen the statistics that the world population is aging. You see here a graph with past estimates and future projections of the population, the percentage of the population aged over 60. In Europe, I think this graph here corresponds to Europe. The top one is projected to have 35% of the population over 60 by the year 2050. So that's a huge challenge. We already see a lot of inflation and labor shortages. So clearly this is very important. In Japan is notorious for its labor shortages. That is only projected to increase as we move into the future, as you see in the graph on the bottom here. So what all this means is that robotics technology as a market is projected to grow quite dramatically. Here you see the projections until 2030, and if my calculations this morning are correct, we're looking at a 12% CAGR, so 12% average growth rate over the next couple of years. So clearly an increasingly important area. So to summarize, robots are a welcome addition to the workforce, and aging population and labor shortages are important motivations for this robotics market growth. Here you see some comparisons between different countries and the robot density, meaning the number of robots per 10,000 employees in the year 2020. And you see countries like South Korea, are at a very high rate, almost 1,000 per 10,000. So almost 1 in 10 employees is a robot, you could say. US still lagging behind these countries, but showing quite a lot of growth over the last few years. Clearly, with the reshoring efforts, that is bound to be ramped up a lot. So robotics will provide a lot of significant benefits. We believe it will enrich individual lives, will help with the boring daily chores, serve to monitor and protect humans, entertain us, and capture interesting experience in our life, and improve society. So it can save lives, whether that's in disaster relief or healthcare applications. Perform the dirty, dull, and dangerous jobs that we would rather not have humans do, improve elderly care, etc. And we think this will expand economies. So it will transform industries, boost productivity, solve shortage of labor, as I just alluded to in some sectors. All right, so one interesting point that I wanted to make is that state-of-the-art robotics is built on generative AI. So we've all seen generative AI being applied to text generation, to image generation, but it's very actively being researched for applications in robotics, among other places at Qualcomm AI Research as well. So if you think about classical robotics, think about a robot in a factory doing the same task over and over. So in those kinds of applications, you have pre-existing scene information, meaning you know exactly what's around you. There's maybe a conveyor belt, there's objects coming in, and the same motion has to be performed over and over and over. On the other hand, where we want to move ultimately is open vocabulary scene understanding. So not having a fixed set of classes that the robot is aware of, that has been trained to recognize, but being generally capable to understand its surrounding, and perhaps assign names to the objects. In classical robotics, there's limited or usually no language understanding involved. Ultimately, for our physical AI companions, we would like to have a natural language interface. Classical robots have pre-programmed reactions. They will always do the same thing in the same context, whereas the future vision, of course, is that the robot will have reasoning capability, common sense, enabled by large language models, and will react in a much more fluid and adaptive manner. In classical robotics, you're often dealing with open loop control, meaning the robot makes a plan and then executes the plan blindly, whereas you would much rather have closed loop control, where the robot is adapting to what actually happens. It might intend to pick up an object, but maybe it didn't grip correctly, immediately detects that and replans automatically. In classical robotics, you're mostly dealing with vision models, and in the future, we'll be dealing with multimodal models, vision, language, perhaps audio, and other modalities as well. Okay, so as I also already mentioned, on-device AI is crucial for robotics. So the primary reason for this is latency. So I think I already said it. If you have a robot that's operating at, let's say, 20 hertz, so 20 times per second, it's making it. It's first of all sensing its environment. It's the sensor data is going through a neural network, typically a pretty large one, and out comes some decision about what to do next, what forces to apply to the actuators, perhaps what messages to communicate to the user, etc. And this happens at a high frequency and has to happen fast, because its motor control is has to be very precise. So there's no time to go to the cloud. So this is where Qualcomm is ideally positioned, I think, to make a difference because of our on-device AI capabilities. Another motivation for doing things on device is privacy. So a lot of cases, this is already true for mobile phones, but it certainly also applies to various kinds of robotics applications. Privacy is very important. You don't necessarily want to send all of the sensor data that your robot is collecting, send it to the cloud. You probably want to keep that local. And finally, a lot of bandwidth is required to send sensor data. Think about video. It's just a large volume of data, and this requires significant bandwidth. And again, Qualcomm is well positioned there, of course, with our 5G capabilities. So all of this motivates AI processing at the edge. And here you see our RB6 platform, which is our main product for robotics applications. It supports the creation of productive, autonomous, and advanced robots. So it features powerful heterogeneous computing capabilities. So not just the CPU, but also other processors that facilitate the running of neural networks, and also other ways of processing sensor input. Can deal with up to 24 cameras. Supports distributed intelligence. So if you have a fleet of robots or drones, can all communicate seamlessly with each other with the cloud. Incorporates the Qualcomm AI engine, which supports up to 200 tera operations per second. High bandwidth 5G, including sub-6 and millimeter wave features, extremely energy efficient, and also has a secure processing unit for vault-like hardware-based security. On top of this hardware platform, we have the Qualcomm AI Stack software system. At the bottom layer, you have your operating systems from Android to Ubuntu, Linux, and other OSs. Various system libraries, drivers, etc. On top of this, math libraries, compilers, programming languages, and finally, the thing that the AI developer actually interfaces with, the AI frameworks from PyTorch to TensorFlow, supporting formats like popular Onyx format, and also incorporating the different the runtimes like the Qualcomm Neural Processing SDK. So it's a full stack solution for on-device AI. All right, so then I will talk a bit about our recent paper on geometric algebra transformers, which is a data-efficient method for geometric data. So this is actually a general method for geometric data. And one of the very important motivations for that is robotics. But you can also think about other applications, like in autonomous driving. Clearly, as you see visualized here beautifully, a lot of the reasoning that has to be done is geometric in nature. You have to reason about the relative position of your car to the various objects, and reason about their motion and so forth. Now, these are not the only problems involving geometric data. Even in wireless communications, the geometry of the physical spaces around you plays an important role in signal propagation. And there are many other problems that of a geometric nature where you would like to apply machine learning. Now, over the last few years, a number of methods have been proposed for processing geometric data with neural networks. And these tend to be very tailored to specific applications. What we aim to do in this work is to build what I said before already, a general purpose solution for geometric data. So we call this the geometric algebra transformer, or GATOR for short. And it incorporates essentially three ideas. The first one is that it takes into account the geometric structure of the data through something called geometric algebra representations and equivariance. I'll go into that a little bit in a second. But basically, this neural network can process not just one type of geometric data, such as a point cloud or the configuration of a robot, or various other things. It is general purpose. You can insert different kinds of geometric quantities, and you can also use it to predict different kinds of geometric quantities. At the same time, it also has the scalability and expressivity of the famous transformer architecture. So the transformer is really taking the world by storm. It's behind all the successful language models, and it's also been shown somewhat surprisingly to be very effective for vision problems, for instance, as well as many other modalities. So it's becoming really the standard neural network architecture for non-geometric problems. And what we're trying to do here is establish such a standard architecture for geometric data, and while preserving the favorable properties of this architecture in terms of scalability and expressivity. So we've done experiments, and we've shown that our method shows very strong performance, even when you feed it little data, which, as I said, is very important in embodied AI, because we have a hard time just downloading data from the internet that is suitable for training embodied AI models. All right, so that's what it is, a universal architecture for geometric data. The three ideas I mentioned, it's based on geometric algebra, which allows us to take as input many kinds of geometric data. It features equivariance, which basically uses our prior knowledge about transformations of the space to reduce the statistical complexity of the problem, meaning we can learn from fewer examples. We can learn more quickly, and it's based on the transformer architecture and the self-attention operation, which is the key part of that. Okay, so first we look at geometric algebra. So if we think about geometric data, it could be anything. It could be the configuration of your robot, or maybe your robot is interacting with some object, like maybe this cube. It has certain parameters that we would like to describe and feed as input to our network so that it can reason about what to do, how to grasp this object, for instance. So how do we parameterize this object? Well, any reasonable engineer might come up with some solution, might say, okay, we have position, orientation of the object, maybe it's moving, it has a certain linear velocity and a rotation. So we put everything together. Maybe if you add everything up, you get about 18 numbers. And you would, in standard deep learning, you would just take these 18 numbers and just plug them into your neural network. Don't tell the neural network anything about the meaning of these numbers, and just train it to process those inputs in order to make a prediction. And that works if you have enough data. But it's turned out to be much more effective to actually group these things together into different separate quantities, and tell the network something about how these quantities transform. So, for instance, your robot might at one point see the object 1 meter away or 2 meters away, and so the object has undergone a translational motion, has undergone a transformation. And by incorporating prior knowledge about how these coefficients describing the geometrical situation, how they change under these transformations, you can make the model much more data efficient. But it still doesn't distinguish all the different types of geometrical quantities. So in this case, we have a position, we have 3 direction vectors, and we have a translation and a rotation. All of those are different kinds of geometrical quantities, and there are different kinds of geometrical computations that make sense for these different types. So for instance, if you have 2 positions, it makes sense to compute the distance between them. But if you have a rotation and another rotation, or a rotation and an orientation, the distance between those things doesn't make any sense. There's certain operations that make sense for certain types of quantities, and building this into the architecture, as we show in this work, is very beneficial. Right. So this allows us to or we want to be more sample efficient by incorporating these types. And the way we do that is using something called geometric algebra. So this is a whole field of mathematics, so I will not go into a lot of details. But the upshot here is that geometric algebra, in particular the projective geometric algebra, provides us with a very convenient way of parameterizing lots of different kinds of geometrical quantities. So all of these quantities are encoded as so-called multivectors, which you can think of as 16-dimensional quantities that, depending on which parts of those which of those 16 numbers you use, you can represent different kinds of objects, like planes, lines, points, and also transformations like translations, rotations, etc. So by using this representation, we can build one network architecture that you can feed different kinds of geometric data. So you can use it in different types of applications. Because the operations that we use inside of the network are also based on geometric algebra, they automatically do computations that are sensible for the particular type of geometric quantity that we input. Okay, so how do we use this in practice? So we have some raw inputs. In a robotic application, they would come directly from your robot. They're typically first pre-processed somehow, and then embedded into this geometric algebra. So they're now embedded into this 16-dimensional space to form a set of multivectors. Those multivectors are then fed to our neural network, the Gator architecture, which always takes multivectors as input and produces multivectors as output. Those multivector outputs are then processed again to extract some relevant quantities that you can then, for instance, feed to your robot to tell it how to move. All right, so the second part here, the second core idea on which this work is based, is the idea of equivariance. So let's go into that a little bit. So in traditional neural networks, particularly convolutional networks, they already use this idea of equivariance, but only for the case of translations. So if you have an image like this dog, we know that for many kinds of problems, if we want to classify this image, for instance, we know that shifting the image, translating it, doesn't change the label. It's still a dog if you shift it. And this prior knowledge is built into the network. So it doesn't need to see lots of dogs in shifted configuration. It automatically knows that those are all the same thing. But classically, this was not done for other transformations like rotations, and particularly in 3 dimensions, where you can translate in 3 directions, you can rotate, you have total 6 degrees of freedom, plus perhaps reflections. These symmetries, as they're called, they start to become very important for data efficiency. So equivariant neural networks, they have a priori understanding of geometry and of these transformations. So they understand that if you're driving your car north with certain cars beside you, then certain driving behavior might be reasonable and others unreasonable. If you rotate the whole situation, you know, it still understands. It doesn't get confused by these things. So mathematically speaking, this property of equivariance can be understood as follows. So we have some in this case points in space, but could be other kinds of geometrical quantities. Then we could apply a transformation, in this case a translation, and then apply our neural network to make a prediction. Or we could start in the top left again, and then first apply our network, and then apply a transformation to the outputs, and we want that the result is the same for both of these cases. If that's the case, then we say that the neural network is equivariant. This equivariance, this puts a constraint on the neural network and therefore reduces the number of parameters that need to be learned. The ideas of equivariance and symmetries, they have already been super important in many areas of physics, where they also provide a strong inductive bias that helps physicists guess the laws of physics. But it also, as we've shown over the last years, has very beneficial effects in machine learning. Okay, so in order to achieve this, we introduce a number of new layers, or blocks, parts out of which the neural network is built. So firstly, all of these, by the way, are the layers that you find in a transformer architecture. So for each of the layers of a transformer, we build an equivariant variant that processes multi-vector data. So there's first of all linear layers. So we have new theoretical results that characterize the equivariant linear maps. There's nonlinearities and normalization layers that are very important. We have equivariant adaptations of that. Geometric layers that include geometric products and other kind of operations that allow us to build MLPs, multi-layer perceptrons, that are an important part of the transformer architecture. And then finally, perhaps the most important part is the attention operation, where different parts of the input can attend to different other parts in order to compute outputs. All right, so that's the final part, the transformer architecture, putting all of these pieces together. So what you see here is the high-level structure of such a neural network. So it typically starts with a linear mapping that takes a sequence of inputs and applies a linear map to each of them, to each of those elements of the sequence. Then we have first a normalization layer, more linear transformations, then an attention operation, another linear operation, followed by so-called skip connection that adds the input back to the output, followed by more layer norm, linear maps, and in our case, a geometric bilinear layer, nonlinearities, and more linear maps, residual connection. This whole transformer block is repeated some number of times. So depending on how large you want to make the network, you repeat this operation several times. And finally, have an output layer that predicts whatever it is you're trying to predict. So first, we did some very simple studies to test this architecture and to highlight the beneficial properties of equivariance and geometric features. So I'm just going to highlight two small experiments that we did. The first is an experiment on embodied dynamics, a famous problem in physics, where you have to predict the time evolution of a number of massive bodies that are exerting gravitational influence on each other. And you can phrase this as a machine learning problem, where you take a lot of samples of the configuration at time 0, and you're trying to predict the configuration after a certain amount of time has passed. And you see here a number of different baselines, from the very simple multi-layer perceptron to certain graph neural networks, the transformer in orange, the very important baseline, of course, and then a number of equivariant methods, the SE3 transformer and SEGNN. Those are previous works from other researchers, and the gator, that's our contribution here. And what we've plotted is on the y-axis the mean absolute error, meaning lower is better. And on the x-axis, we plot the number of training samples from 100 to 100,000. So as you can see, the gator already at 100 samples achieves a very good mean absolute error. On the other hand, a transformer, which I think is the most interesting baseline to look at, it does very poorly when you give it a small amount of data. This is not any new result. People are excited about transformers because if you give them enough data, they just keep getting better and better and better and better until eventually they will also get to the same level of performance, presumably, but it can take a long time. It can take a lot of data. So you see here very clearly in this toy experiment that our architecture enjoys a lot of great data efficiency. We also tested it on another off-the-shelf data set where the task is to predict artery wall shear stress. It's actually a medical application. This is not really a core interest for Qualcomm, but it's a simple test that we could just run our architecture on to again show the data efficiency, and also I think to make the case that this is really a general purpose architecture. We did not design this thing just to do robot motion planning, which I'll talk about next, but it can do a lot of different things. So it outperforms state-of-the-art results with far less data on this wall shear stress problem. Then how are we going to use this for robot motion planning? Well, the idea is to understand the idea, we first need to understand the idea of diffusion. So what you see here on the left, sorry, let me replay the animation here. What you see here on the left is a demo released by Qualcomm AI Research, where we were the first to run stable diffusion image generation on a mobile phone. And the way that this works is that you start out with random noise. So each pixel is randomly sampled. It just looks like pure noise. There's a text prompt that gets encoded by a neural network. And then there is a denoising network, which conditioned on this text prompt will basically look at the noise and try to spot some patterns in it and enhance the image, make it a little bit less noisy. And then the slightly denoised image is again fed into this denoising network and is again denoised and again and again. And after a while, as you saw in the animation, you can get these extremely sharp, realistic looking images that actually correspond to the prompt. So what does that have to do with robot motion planning? Well, the idea here is that we don't diffuse an image, but we diffuse a robot trajectory. So here you see sort of an illustration to explain the idea. We see the whole trajectory in the beginning, and you see all these points. They're kind of randomly sampled. They're very noisy. And over time, as I play this animation, this trajectory is denoised. So gradually, it starts to look more and more like a realistic trajectory. So that's the idea of this method. We have a data set of robotic trajectories of the robot performing certain actions that we want to learn from. Could be executed by humans controlling the robot, either physically if it's a cobot or through a controller, or it could be some other control method. Could be, there are many ways to obtain this data, but we assume we have such a data set. And what we're going to do is we're going to train a diffusion model to model those trajectories. So we apply this to robotic motion planning. And firstly, we have here this robotic block stacking benchmark. This is a so-called KUKA robotic gripper, and it's simulated in a software package called PyBullet, which does the physics and also the graphics we have. This was proposed by a paper from UC Berkeley last year. So as I mentioned, it's an imitation learning setting. So we have 10,000 expert trajectories where the trajectory consists of the state of the robot, the state of the blocks, and the action taken at each time step. As I mentioned, we model these trajectories with a diffusion model. And now the crux is the denoising network of this diffusion model this model that takes the noisy trajectory and produces a slightly less noisy trajectory repeatedly. That is going to be a geometric algebra transformer because the inputs are geometric data and the outputs are geometric data, so it makes sense to use this kind of architecture. And yeah, here you see the robot successfully grabbing and stacking a number of blocks in simulation. So here again, we have a number of results. So we have a similar plot. Now we plot on the y-axis the performance, which is essentially the percentage of trials where the stacking is successful. And on the x-axis, we plot the size of the data set again. So in this case, higher is better. And you see that the geometric algebra transformer, if you compare it, for instance, to the diffusion model, but based on a regular transformer, you see our method outperforms significantly. In fact, this is a logarithmic plot. So you see at 100 samples, our method is already outperforming the transformer with 100 times more data. So that's a very significant saving in terms of data that needs to be collected. Right, and we have various other baselines. So you can check out the paper if you're curious. Now, another very important component is of any method in today's age is scalability. So, is the model able to process very large amounts of data, long sequences, for instance? Now, when you scale up the sequence length in a transformer, actually the compute cost grows quadratically. So that's what we see here in the bottom plot. We see the transformer in this plot lower is better. So it starts off costing not a lot, and then at some point it starts growing. You see a straight line on a logarithmic plot, log-log plot, meaning in this case a quadratic growth. And you see the gator performance asymptotically is equivalent to the transformer because the cost of the computation is dominated by the attention operation, which is exactly the same in our method and in the transformer. There's some discrepancy, as you can see, at smaller sequences, shorter sequences, but this is more an artifact of our current implementation. This can probably be optimized away, if we can get better GPU utilization. You see here some of the other equivariant baselines, they fare far worse. And especially when we look at memory in the top plot, we see that now the transformers, they actually have linear growth in memory with sequence length, corresponding to this shallow slope. Whereas the other methods have quadratic growth. This linear growth is actually because of a recent breakthrough in the implementation of attention called flash attention, also implemented in the XFormers library that we use. So the point here is we are able to leverage all the innovation that has gone into optimizing the transformer architecture. All of that is also now applicable to our geometric deep learning method. Right. So a little bit peek into the future is that we are working on running this method on a real robot. What you see here is actually not yet our algorithm operating it, but we are in the process of making that work. So it's very exciting, and stay tuned for that. Now we do have one more project, but I'll go over this fairly quickly. So this is about uncertainty-driven affordance discovery for efficient exploration and learning of affordance maps. Now, this word affordance is a word from psychology or cognitive science that basically indicates the answer to the question, what can I do in this situation? There are different kinds of actions that we can do. I can open a door, but that is an action only applicable in a certain situation. And this kind of understanding is going to be very important for embodied AI. So we have here a method that learns these affordances in a very data efficient way by reasoning about its own uncertainty. So we have a situation here represented as a 2D point cloud. It gets encoded. Then we have an ensemble of decoders, each of which has a slightly different belief about which affordances are available in this situation. Using something called the information radius, we can quantify that and figure out which actions have the highest uncertainty. So we are incentivized to try out those actions in order to reduce uncertainty and to learn more efficiently. And using this method, we've shown that we can learn these affordances very efficiently. So we have some experimental results where we plot the number of interactions on the x-axis and the success of grasping essentially on the y-axis. And you see that our methods in blue and green, they are again outperforming various other baselines. We have this here for real world objects, real world grasping as well, where clearly you don't want to have to do a million trials in order to learn how to grasp certain objects. And this seems to work very well for speeding up that process. All right, we're almost at the end, so let's go over the sort of the high-level takeaways. So embodied AI will benefit society in manufacturing, healthcare, and other areas. We think on-device generative AI is crucial for embodied AI. Equivariance allows for more efficient understanding of 3D images and videos with AI, which is particularly important for embodied AI applications because data is often scarce. And Qualcomm AI Research has achieved state-of-the-art results in data-efficient robot motion planning. Thank you for your attention. If you want to connect with us, check out our research page, our blog, our Twitter /X page, or YouTube page. Yeah, I'm happy to take any questions from the audience. Thanks.
Thank you, Taco. You can actually stop sharing now, and we can go back to the main screen. So thank you very much for your presentation today. What your team is working on is very interesting, and I was just curious. There's an emphasis right on data efficiency that you mentioned, and is it the case that with Gator, data sets for robotics will become obsolete or unnecessary? What are your thoughts on that?
No. I think data sets will always be very important. But the way I think about it is how much bang do you get for your buck? So if I double the size of my data set, does my performance improve 1% or 10%? That's a big difference. So that's where we are focused on when it comes to methodological research. How do we make the added data actually count? But data will always be important. One thing I didn't mention in the talk, but that's also a very active area of research in Qualcomm, is actually using internet AI to help embodied AI. So in internet AI, as I mentioned, we have tons of data available, and we have also pre-trained models. So they're either whether it's done by Qualcomm or by other parties open sourcing these models, someone goes and downloads a lot of text or a lot of images and video, trains what's called a foundation model on this, a generative model of this modality. And we are looking at, okay, these models, they clearly have a lot of understanding about the world already. So for example, multimodal image text models, they can generate images corresponding to text that you input. So they understand some correspondence. Now, if I want to make a robot that actually understands my commands that I express in natural language, it seems plausible that using that understanding that these foundation models have is going to be beneficial. So one thing that we are investigating is how to actually use those foundation models to benefit embodied AI. And there, clearly the large data sets are always going to be essential.
Yeah. All right, quite a few questions are coming in. I don't know if you can see them on your end, but all right, we have some questions about equivariance. So I'm going to ask one of them. So how do you learn the equivariance from sensory motor data? And have you thought about cross-model generation?
Sorry, what was the first part? I didn't hear that.
How do you learn the equivariance from sensory motor data?
That's a very good question. Yeah. So in the robot motion planning application, we work with a data set where the robot's configuration is represented. Well, you can represent it in different ways, but it's represented, for instance, as joint coordinates or things like that. Similarly, for the object's position and orientation is given. And when you have only a camera, for instance, then going from the raw sensor data to these geometric quantities, that's still a challenge in itself. Now, Qualcomm has a very active program on perception, where we use deep learning techniques to process visual data, data from range sensors, point clouds, etc., even radar and other modalities. So we definitely have a lot of expertise on this. For our particular project, we have some ideas on how to actually learn this mapping from sensory data into a latent space that can be processed by an architecture like Gator. But this is ongoing research, so stay tuned.
Yeah. Right. I have a question, actually. This is about the applications of Gator. Is there an application of path planning to automotive or other types of trajectory planning that you can think of?
That's very well possible, yes. So Gator is something that we've released fairly recently. It was developed with, robotics and embodied AI as the primary motivation, but also with the idea that this should be more broadly applicable. So we have had some conversations with folks in the automotive team, and so it's very well possible that we can apply the method there as well. But again, that's all. That's not yet ready for prime time.
Makes sense. So we'll stay tuned. All right, we have a question about perceptual principles. Do you incorporate perceptual principles? Examples given are egocentric cores, gestalt completion, object permanence over time.
Yeah, so I think you're yes. I've read quite a bit of cognitive psychology where these things play a big role. Object permanence is an understanding that arises in young children at a very particular age. They suddenly understand that if you hide an object, it's still there and it's supposed to reappear. And if it disappears behind another object, then they're very surprised, as they should be. And there's actually ample evidence that this kind of understanding is partly innate. So we are wired to understand those things, which also goes to the point about data efficiency. So humans, we don't have to read the entire internet to learn how to read. We don't have to watch trillions of hours of video to learn to see. So there's a certain data efficiency which comes from having a priori understanding of certain things, including object permanence and other priors. So our research program, broadly speaking, is indeed philosophically aligned with that, and that we are building in prior knowledge about geometry in order to improve data efficiency. But object permanence specifically is not something that we have put in. So I think there's probably a lot of psychology-inspired research that is still to be done that that might prove fruitful. On the other hand, from a sort of very pragmatic engineering perspective, yes, data efficiency is important, also especially for embodied AI, as I've argued. But sometimes it's actually just more practical to just pay up and collect more data and get better performance in this way without trying to be too clever, because being too clever can sometimes also backfire. So anyway, I think it's an interesting research problem, and it's worth exploring, and which we'll also continue to do while also continuing to scale up data sets.
Yeah, we're almost at the end of our webinar. I see some questions are still coming in. We're going to try to also reply to them after the webinar in the Q&A box. If you could just give us a sense for some future directions or use cases that you're seeing for equivariance. I know we already touched upon it a little bit, but if you could, if you could tell us a bit more about what you're seeing as what you have as your vision for that in the future.
Well, when it comes to equivariance and geometric deep learning broadly, outside of Qualcomm, but just looking at the research field more broadly, one area that's really gaining a lot of traction is various applications to do with physics and chemistry. When you want to predict properties of molecules, for instance, for materials design, for drug design, for the analysis of proteins in the human body. That's where equivariant networks are being applied a lot, and lots of very exciting applications there. In Qualcomm, you should think about perception of the three-dimensional world, action as in embodied AI and robotics, but also autonomous driving, and wireless communications, as I mentioned, is also inherently a geometric. It's partly a geometric problem. So we're looking at all of those, and I think the future is full of exciting possibilities.
Thank you very much, Taco, and keep up the good work. Thank you, everyone, for joining us. And you have the presentation as well as some useful resources that you can download. This webinar will also be available on demand. Thank you, and have a nice rest of your day.